So hello, everybody. Welcome to the fourth lecture on open quantum systems. And a week ago, we talked about density matrices, superoperators, and unitary maps, which are basically superoperator version of unitary evolution maps. And we skipped part about matrix representation for superoperators, and I promised I will do it in the beginning of this lecture, but I changed my mind. Okay, we'll skip straight to this third segment, second segment of the lecture, the stochastic dynamics of quantum systems, and next week we will get to the point where we want to use the matrix representation. So that would be a great point to actually bring it up again. So yeah, so we go straight to next big segment. So yeah, stochastic dynamics of quantum systems. So before we talk about actual quantum systems and then dynamics, first, I want to do with you like a basic review of theory of stochastic, of probability theory, stochastic processes and stuff like that. Maybe it will be just a refresher for some of you, or maybe it will be completely new for someone. Whatever the case, you can treat it as a bonus feature, right? All right, so yeah. So to talk about theory of probability, I want to start with stochastic variables. Okay, so what is stochastic variable? So formally, stochastic variable, which I will denote them with a capital letters, like X, for example, will be also using small letters. So for example, small x, I will try to write it like this to avoid confusion. So not only smaller, but also different shape. So formally speaking, okay, stochastic variable is a map, okay, is a function. Is a function from the set of, so this is a set of outcomes of a random event. So what is a random event? Well, it could be almost anything. For example, a coin toss is something that we will say is a random event. And actually, in case of coin toss, so for example, coin toss. So omega of coin, that would be something, a set composed of two elements. So because you toss a coin and you get either heads or tails. Okay, so that would be a simple two element set. And okay, so random variable takes this as an input and maps it to real numbers, let's say. Okay. So what is the purpose? Okay, so for coins, stochastic variable for coins would be simply x coin. Then that would be, it would have to define the mapping. If you get heads, you map it to some value x h. If it's tails, you map it to some value xt. Okay, quite simple. Okay, so what is the purpose behind this this definition? Where, so you see, this random event is something like a coin toss, something not abstract, but actually the opposite, something very tangible, right? And you want to have some tools to inject this thing like coin toss into your standard mathematical formalism, okay? And this is why you introduce those variables, which basically correlate some numbers with outcomes of this random event. So stochastic variable itself, it's important to remember, stochastic variable itself is not a number, okay? It's a map. So in practice, you use it as a like a placeholder, right? You put it into your mathematical expression, and until the event happens and you get some outcome, it's just it's just a symbol there. But once the event happens and you have some specific outcome, it converts into a number. Okay, so you put it into your expressions as a placeholder. So, for example, if we take some generic function from real numbers to real numbers, okay? So standard way of operating with function f would be to feed it with some input, right? We feed it with input and some input x, right? And it gives us value, output f of x, right? But now what you can do, you can take your function and feed it with your stochastic variable, okay? In this way, you create a new stochastic variable that's like it's processing the information injected through x further, okay? Just further processing. So if you put here, let's say x coin, we would get a new stochastic variable that would assign to heads value f of x h, right? Tails would assign value f of x t, and so on. So this mode of use, let's say this mode of operation, when you just put stochastic variables into your expressions and just wait for the events to happen, it's not a typical way of using them, although it's sometimes you do use it like that. But more practical way to use them is to okay, in more practical scenarios, you don't really want to see this like dynamical this dynamics of events happening and converting to some outcomes, but you want to quantify some properties of this random event. You want to in some way capture its nature. The things that it has. There are multiple outcomes. There is randomness to it and stuff like that. And you want to capture it, quantify it in such a way that it still can be incorporated in your standard maths. So the industry standard way of doing that is to, rather than talking about event itself, you want which could be some complicated physical process like coin toss, you try to condense it into into probabilities of obtaining certain outcomes. Okay, so let me see my notes. Where am I? Right. Right. So right. So rather than talking about describing the course of the process of this event that happens, you condense all this information into relative frequencies of different outcomes happening. And since we introduce stochastic variables, which bring another level of abstraction, but instead of those outcomes are now correlated with some numbers, so we can just skip straight to talking about probabilities of variable acquiring a certain value, okay, which is correlated to event giving you a certain outcome when it happens. So this brings us to the concept which you are probably very familiar of, probability distributions of stochastic variable that represents some random event, okay? So probability distribution of stochastic variable X. So we would denote those guys as P superscript X, capital X, to indicate that it's associated with the stochastic variable, and it's a function, right? So it takes numbers as inputs. And the inputs the probability distribution accepts, so the domain of this function P is actually the image of the stochastic variable, right? So it accepts all the possible values capital X can convert to, right? So we would say that domain, so I guess dom of P of X equals image of capital X, right? So in case of if coin toss, so our coin example, right? So the domain of PX coin would be simply XH and XT. So that would be a discrete domain, in this case, 2 elements. But the convention, the standard convention, is to actually, like, rather than remembering what is the actual domain of your probability distribution, you could just extend it to all the values and simply set for all the inputs outside the image of your stochastic variable, you just set P to be 0. Okay, so it's like you can, so you don't have to write in your integrals, integral over a domain, which is a set, blah, blah, blah. You just integrate over whole real line and just remember that the probability for values outside the domain, this image of X is just a 0. And this is the convention we'll adopt here. What else? Okay, so this is a inputs the P accepts, but what about the values? What kind of values it assigns to each input? And roughly speaking, or intuitively speaking, to determine the value, so the probability, you can, like, imagine doing finding it out through experiment. So you basically consider a trial where you instantiate your event n times. Okay, so you have n times n events. Then you count the number. So you instantiate n events, and you count the number of instances where capital X converts to value you are interested in. So count the number of when X equals some X, okay? Divide it through n over n, and take a limit n goes to infinity. Okay, and this would be the value of P of X. So in other words, it's like a relative frequency of given outcome happening in very infinitely long trial of instantiating your event. So in case of coin, if we imagine that the coin is fair, right? So then you do a long enough trial, there would be the equal number of heads and tails. So that would mean that for coin, PX coin of X tails would be equal to P coin of X heads, and they would be equal to 1/2, all right? Because in trial of n, n/2 will be heads, n/2 will be tails, divide by n, that's 1/2. And so this is how you would like determine the what probabilities you would assign to each value. Okay, so now, given this rough description of what the probability distributions do, we can quite easily identify like what are the properties, defining properties of those functions. So properties of prob distributions. There are two properties. One would be that Px is non-negative. Negative only or in formulas, we would write it that it's greater or equal 0. And why? Because the value you figure it out by counting the events, right? So counting is always a positive number. The second is Px is normalized. It's normalized to unity. Unity, which in formulas means that you either integrate Px dx equals 1. So this is when image of X is continuous on knows, so like a interval or something like that, or you sum over X belonging to image of capital X equals 1 when image of X is discrete. Like with coin, right? So either you switch between integrals or sums, depending on what kind of variable you're dealing with. And why it's normalized? Well, if you in any trial of n instances of the event, there will always be n outcomes of any kind, right? So we can count all the possible outcomes divided by n. That's 1. It's unity.
And just give the first one.
Yeah. I mean, yeah, sure, of course. If you want to be super fancy, maybe it's not that fancy, right? You can always introduce distributions. If you go beyond functions and use distributions, you can use Dirac deltas to have a discrete image, but still using integrals. Yeah. Well, actually, we will be using Dirac deltas soon, so maybe, whatever floats your boat here. Okay, it's you can use however fancy mathematical tools you are comfortable with. So and also conversely, if you have any function of X that's satisfied those two conditions, so it's non-negative and normalized, it can serve as a probability distribution for some stochastic variable. Okay, so this is like any probability distribution satisfied this, but also any function satisfying these two conditions can be a probability distribution. All right, so once you have your probability distribution, now you can like answer a lot of questions about the statistics of your stochastic variable, and by proxy of the random event that's correlated with your variable. So one example would be a, let's say, a probability. If you want to have probability of that when the event happens, it will convert our variable into a value x that's greater than some x0. You can ask this kind of question, and the answer is you can obtain it by taking your probability distribution and just integrating it like this. Or, you know, if you have a discrete distribution, just sum it over, right? Instead of integrating. So that's one way to use them to calculate probabilities of certain events happening, right? Like you know, getting x greater than some x0. But there is a class. There's important and useful class of quantities derived from distributions that's called expectation values. Expectation values. This is the important class. The simplest one is the, how do I call it? The average value. The simplest one would be average value. Average value. Well, which I will denote as capital X, so our variable and bar above. Okay. And it's defined as you take integral x px x dx. So what this thing represents? So this average value x bar is a estimate. How did they word it here? Okay, is an estimate for the arithmetic average of a large number of samples of stochastic variable x. Okay, so in other words, in human speak, so x bar is a value around which the stochastic variable will scatter when you convert them into numbers, right? So you were tossing your coin or tossing your coin, right? And you will get HT, XH, XT, and they will scatter around X bar, which in this case would be actually 1/2, which we could even calculate easily. So for example, X coin bar. So that would be, of course, it's discrete. So rather than integration, we'll have sum. So we'll have sum over xt, xh, x, px coin, x. So so that would be xt px coin xt. Okay, that's too much. It's already written here. That would be xt times 1/2, right? Plus xh times 1/2, which is simply xt plus xh divided by 2. So that's the average value, and now you toss your coins, you get either xt or xh. So they will be either above or below this average value, right? So you will get this scattering like that. So in case of coin, this is not very helpful quantity, but you can imagine more advanced stochastic variables. It's a pretty important piece of information about the distribution. So like I said, average value is the value around which you scatter, and the extent of the scattering can be estimated with another expectation value, the dispersion. Dispersion, which is given by, so capital X square minus average square averaged, which in terms of formulas, this means that you take your distribution, just submit x square, x oh, sorry. I meant to write something else here. So I just realized I have a boo-boo in my notes. So what I wanted to write is x minus x bar squared averaged. Okay, so this is like the so this looks like a dispersion, like the extent of scattering from the average, the difference between the average value and the value of your variable squared, right? In that case, I never know. It's dispersion or I don't know, because one is the square root of the other, and
Square root of variance.
oh, that's even better. So this is variance.
I think it's square.
Okay, and this, what is dispersion then? Whatever.
Maybe it is the same.
Oh, maybe it is the same. I think I checked that like a couple of years ago, but
Maybe one.
so so dispersion slash variance, however you call it, it's not super important. What is important is that this is how you quantify this scattering around the average value. If you take square root or whatever, it's just a matter of choosing your units. Okay, so this is what I wanted to write. This average value isn't just a number, it's a constant, right? So the integration doesn't care about it. So you can just, this is like the standard trick you use with this formula. Twice x times constant average plus square, okay? So then you get x square px dx from the first term. The second term, minus 2x, this is constant, so I can stick it outside the integration. Dx, right? Plus x bar square. But this dude here, that's just x bar, right? So this whole guy here is just minus 2x bar square. right? So it will, this dude will cancel with this dude partially. So you will get x squared. So unnatural to me to write this in this font. Dx minus x bar, which I can write as x squared minus x bar square px x dx. Why I can do this? Because I can always multiply this by 1. And 1 is, because I have normalization, I can write it like this, right? And then just absorb constant under the sign of integral. This is how I arrive at this point, which is equal to x minus x bar square bar. This is a cute little algebraic property of expectation values. And in general, you can calculate this kind of expectation value of any function of x. So you can have some f of capital X bar, which you would define this function f of x and the distribution. And of course, the interpretation of this kind of expectation value depends on the shape of function f. But this is a procedure you can always do here. And this is a typical way of dealing with or using probability distributions. You use them to calculate averages, which then means something to you, hopefully, or sometimes even without any meaning, just for fun. Okay, so that would be to summarize, we have thing that we would call random events, which could be like a coin toss or some tangible physical process, very complicated. But the thing about random event is that it can have many outcomes, and there is randomness to it, right? That those outcomes occur with some relative frequencies to each other, right? So then to incorporate those, to describe those events with our maths, standard maths, we introduce those stochastic variables which correlate outcomes of event to numbers, right? So every outcome can be assigned with some number, and we know how to work with numbers. And now we can use those variables raw, right? So just put them into our expressions and wait for the event to happen. Or we can talk about probabilities of different outcomes happening, right? So this led us to probability distributions, which basically quantify this relative frequency between outcomes, right? And so instead of using the variable itself, you can use this function P, probability distribution, that characterizes what will happen, what happens with this variable, or by proxy the event. And once you have this function in your hands, you can like ask all the questions about the statistics of your variable, of your event. And one of the questions you will be asking all the time is expectation values of various functions of x. So that was the quick rundown. And now we proceed to next step. 312, stochastic processes. Stochastic processes. probably, okay, once, good. All right, so we had stochastic variables, which assign the outcome of the event a number. Stochastic process is like a extension of this idea. So stochastic process, which I would denote also with capital letter, but I will also write this like a function of t. Treat it as a symbol for now, okay? I don't mean any specific time t here. It's just capital letter with a function of t. And this guy, it takes a outcome of event, and rather than assigning it just a number, it assigns it's a whole function of time. Oh, well, of some parameter, which typically is interpreted as time. So you would write it that stochastic process, you take your space of outcomes and you assign it a whole function, which I will denote it like this, okay? Just to remind us, this is the whole function. We have a variable that is a function itself, okay? So this is like, if you're familiar with, if you did some programming in, let's say, Python or any modern language, you're probably aware of lambda functions or anonymous functions, right? Where you have a variable that is actually function itself. So this is like this is the same kind of notation, if you can imagine that, right?
Those aren't unique to Python. There are not many languages that actually have them.
I think like all of them have this. JavaScript has it, PHP has it, Python has it, C# has it, probably C++ also has it. Okay, C++ might not have it because it's old.
You can make that. You have a point of the function that would be a like variable and the function.
Okay. Okay. But you know,
C++ has changed very much.
Does it have lambdas?
It might have, but I think like the now 2023 version might have it. It has changed so much that we cannot imagine that.
Yeah, that is true. It has evolved a lot, right, over the years. So this is a good, this is a very useful tool to have lambda functions. And of course, there are whole languages that just basic functional programming, right? So everything is lambda functions, right? So this is like stochastic process is a, right, so it's like stochastic process is a stochastic variable, but it's its image are lambda functions, okay? So are anonymous functions, which are called typically, so this would be a trajectory of the process. The process. So I hope this is not super confusing. So in other words, so we have your event, could be coin toss, could be something else. When the event happens, you get a functions. You get a function response, which you can then feed with your argument, time, for example, or just plot it, whatever. It's not numbers, whole function. So there is more to it. And this is, of course, again, we can talk about probability distributions for our stochastic processes, but now those probability distributions, well, they have to accept an argument that is a function. So you would have a function that is function of functions, which in nomenclature, mathematical nomenclature is called functional. Not super function, unfortunately, but a functional. So we would have probability distributions for stochastic process. So we will denote it with a, rather than a round brackets, you use a square brackets. That's the word I wanted to find. right? So square bracket distinguishes functionals, super functions from normal functions. And again, this guy, it's a probability distribution, so it has to be non-negative. So this guy has to be non-negative for all trajectories. Okay, so I will stick to my oath to use lambda notation. Okay, so non-negative and normalized. So you take your you integrate your distribution, but you integrate over all trajectories. So this is a functional integration. Integral. Which sounds super scary because it is quite scary, but it's a thing, okay? Yeah, big D, and to be even more transparent, I also will put it in a bracket, okay? It's big D and with brackets around. It's a functional integration. Super scary. You probably will never be forced to actually calculate. It's like, you know, Riemann sum to approximate. That's that one. I mean, there are ways to calculate functional integrals like numerically, of course, but it's super complicated. Okay, but symbolically, it behaves like a standard integral. Okay, it's have the properties of standard integral just over a space of functions, which is like, you know, a thing. But symbolically, it's all fine. However, again, symbolically it's fine, formally it's fine, but in practice it's like it's not very useful. Okay, you can prove some theorems using this, but if you actually want to calculate anything, that's not what you use in practice. In practice, in most cases, you can always deal with your problems using so-called joint probability distributions, which are derived from this master functional probability distribution. So joint probability the joint probability distributions are a whole infinite family of standard functions. So let me introduce notation. So they are a multivariate probability distributions. Okay, so rather than depending on one argument, it has n arguments, and n can go to infinity easily, and they will be indexed by time. Okay, and just to shorten the notation, I will use I will use a n tuple notation for sequences. So I will write Tn and the underline Fn, and this means Fn underline means that this is a sequence Fn minus 1, blah 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 blah, F2, F1. Okay, so this is an n tuple of length n, and the subscript just informs us how many elements the tuple has. And I will always assume that the times are ordered here. Okay. So T1 is the most in the past, Tn is the most in the future, and all the things in between. And so these are standard probability, multivariate probability distributions, so non-negative and normalized. Normalized in the sense that you take a PF Tn Fn and you integrate it over Fn. So you do the n-fold integration, right? Minus 2 plus infinity, and this is 1. Normalized in this sense for each n, for each time indices actually. And those guys, what is their interpretation? So this functional probability distribution is like a relative frequency of getting a given trajectory, given function. So its interpretation is the same as the interpretation of probability distributions for stochastic variables, right? Is the same thing. But with these guys, you can think of them as a probability that trajectories of our process will pass through value f1 at time t1. So in other words, that f at t1 equals f1, then it will pass through value f2, value f3, and so on until you have passing through value fn, right? So formally, those joint distributions are so they are of course derived from the functional distribution, this pf of square brackets, and formally you can treat them as a restriction of this functional distribution, which in other words it's a integral j from 1 to n delta Dirac delta. So we are using Dirac deltas. J PF F df, right? So this is like a formally you call this restriction of the distribution, this functional distribution. Restriction because you are imposing constraint on this distribution, right? Which spits out, impose a constraint. The constraint is that at the time tj value must be fj, right? So when you impose those constraints, you obtain probability distributions, but now it will be a discretized version of this functional distribution, okay? I mean, discretized in the sense that it's on discrete time grid rather than whole domain of the trajectory. So a way to visualize this, a helpful way to visualize this imposing constraints is with this so imagine you have a shutter, okay, something that can close instantly, right? And you can make it so that it closes at at given time it closes so that it almost closes completely, but it leaves a small slit at the coordinate fj, for example. So you can make it at time tj, the shutter closes, it leaves this very small gap at the coordinate, at the value fj, right? So you can make an obstacle course for trajectories in this way, right? So if I draw it, so let's draw a space-time diagram, let's say. So here will be the values of f, here will be time, and we have our shutters So let's say at time t1, we want to close the shutter, almost close it, but we leave a gap at value f1, okay? Then at time t2, let's say we will close it like that. That would be a value f2, and so on, right? And now you take you draw at random trajectories from your distribution PF, from this guy, right? And the probability, I mean, this obstacle course will block almost all the paths except for those that actually happened to like pass through the slits we left open, right? Something like that. So those multi-time probabilities, PTN, Fn, is basically a probability that a randomly chosen trajectory will pass through all the obstacles, okay? Which in formulas, it means this or this, okay? Is it clear picture? Maybe not super clear. A little bit clear, okay. I mean, this guy, right? So how to say it? I always think of it as a because you know what this guy means. It's like you take all the trajectories, you integrate over all trajectories. So you plop them in, right? You use all of them. You weight them with a probability distribution PF, right? But now there is this other term. I always think of it as a constraint that I'm selecting. On top of that, I'm selecting only those trajectories that satisfy this condition, right? So at time tj, this trajectory has specific value fj, right? So I'm filtering the options, right? And then so this gives me like yes, this is direct delta. So that was the question. Okay, so okay, now it's clear. Okay, so this is direct delta. Direct delta. Right. So we use the distributions anyway. So this is direct delta.
It was really part of the question, but the rest of it was enough.
Okay. So sorry, I unnecessarily wasted your time with this over explaining. Okay, good. This is like once you get used to this, it's all natural, but you have to get used to it first. What else? What else? Okay, so one more thing so you basically, so what I'm advocating here, or I'm showing you, is that you can take your stochastic process and like describe it, quantify it with this master probability distribution on space of trajectories, on space of functions, or you can like switch to the infinite family of normal probability distributions, those joint probability distributions. It's an equivalent description, which you can switch between, okay? And here the benefit is that you have this one master object, right? One distribution that governs all. And here you have whole hierarchy of distributions, which is like less nice, I guess, but you are dealing with normal functions, okay? Which you know how to integrate and how to do all the stuff with. So it's like you get something, but you lose something, right? But this is more practical. To use this is more practical. And of course, this family of functions is not like completely unconstrained, right? It's not just normalized and non-negative. They are, they are equivalent to, they are derived from this functional distribution. So there is some property will linger of this operation, of this taking restriction. And the property that lingers is quite important thing in the theory of probability or stochastic processes, something that's called Kolmogorov that's the important mathematician, the consistency condition. I wrote the Kolmogorov in parentheses because usually consistency conditions is enough. You don't have to quantify it with Kolmogorov, but just to be safe. And what this consistency condition is it tells us that those multi-time probability distributions, they are related to each other in a very specific way. It's like you take one of them, any one of them, and you marginalize it over any variable, okay, any argument, whichever you wish. And once you do the marginalization, you actually obtain multi-time distribution again, where the guy you marginalize over is just absent. You can just strike it out. So I will denote it like this. So this is the n-fold, so n time distribution, and this on the right-hand side you have n-1 times here, okay? So it's also one of the multi-time distributions for our process, but with tj time missing, okay? And this is non-trivial property, although once you inspect this relation here, the origin, okay, you look at this thing, it's easy to see from this why you have this relation, right? Because I have this formula and I integrate over fj, let's say, one of those guys. So this integral will just consume the delta. So there will be a product of deltas where the one I integrated over is just missing. And that's just definition of multi-time probability with this particular time argument just gone. So this is very simple. So in this way, in this direction is very easy to see, but there is more power to it because it turns out that any infinite family of multi-time probabilities that satisfy consistency condition, okay, they can be extended into this functional distribution. By extended, I mean that you can do something like take the limit in quotation marks of this sequence going to like a whole interval, let's say. Okay, so imagine you have your discrete time grid, you have n time points, and now you want to like make it more and more dense, and you want to go to infinity so that it's so dense that it's actually whole interval, right? It sounds like super crazy kind of limit, but it actually, when you have consistency condition, I lost my, oh, here it is. When you have your consistency condition, this limit actually makes sense, and you can perform it, and you get a unique probability distribution on space of functions. And this is so in this direction. So from the family of multi-time probability distributions, you go to stochastic process. So the functional distribution. This is Kolmogorov extension theorem. It's called. It's one of the foundational theorems of theory of stochastic processes. So this is extension theorem. So that's like the math bit. So consistency condition. So this is like a mathematical. So this would be a mathematical consequence, but you can do. We can still like explain this formula, why it's here, why it's kind of natural for it to be here with this our invention of those shutters. Okay, so if you think in this picture of shutters, so if you have probability, it has argument at time tj, right? So this guy tells us this is a probability that the trajectories will pass through this shutter that closes at time tj at coordinate fj, right? So this probability that you time tj, you have fj, and the guys just went through. So now if I take pf tj fj and add to it pf tj with some fj prime, what's this? What this thing means? So this is basically a probability that at time tj you close your shutter. I mean, you open your shutter, you leave two slits rather than one. G prime. So this is a probability that for your trajectories to go through here or go through here. You open more options. More trajectories can pass through. So now you imagine you add more terms, you open more slits, you let more trajectories pass through, and once you go all in and you just integrate over all possible coordinates, you basically open the shutter wide. Okay, you open it wide, so it's like as if there was no shutter at all. Everything can pass through. But if there is no shutter, there's no constraint at time tj effectively, well, that's just multi-time probability where there is no argument at time tj. So in this sense, you can like, if you have this trajectory picture in your mind, that you have trajectories and they have to pass through somewhere at any given time point, this like consistency condition becomes natural, essentially. So so these are joint probability distributions. Okay, so I promised you that they are good for practical uses. So let me show you why they are so useful. So again, we have a stochastic process, we have probability distributions. So again, expectation values. Your distributions, you will use expectation values for sure. Then you of course have a stochastic process version of expectation values. So for example, the average which I will write it like that. And formally that would be F T1 PF dF. Right, so the average value of the process at time and some specified time T1, it's basically like the the arithmetic average weighted, where the trajectories, the values of trajectories at time T1 are weighted by the probability of getting this given trajectory, right? So this formula essentially, but you can obtain it in other way. You can, rather than getting the value of trajectory f at t1 and weight it by probability of getting the given trajectory, you can say like, okay, I can take a value f1 and weight it with probabilities that trajectories, randomly chosen trajectory passes through this value at time t1. So in other words, PF T1 F1 dF1. Okay, and these guys are equal. Right, this is the same thing, and you can actually, if words don't convince you, if my word salad I just spit at you doesn't sound convincing, we can of course show it through maths. And so let me show it to you. So we start with this basic definition, dF. And now I will again use Dirac deltas, because why not? Because this value, I can be very cheeky and write it as F1 delta F1 minus FT1. Do I have agreement about this trick, this sleight of hand? So, right? Looks good, right? Nothing suspicious here. But now I can exchange the order of integration here, and to before there will be questions, is it legal to exchange the order? Yes, it's legal, and it's legal because of Kolmogorov extension theorem. Things are uniformly bounded in an appropriate way, so you can exchange the order. It's legal. So I can exchange the order of integration. F1 PF F dF, close parenthesis, dF1. But what is this guy? That's the joint probability distribution. PF T1 F1 dF. Oh, okay, so that's this is it. Okay, what else? Okay, I will skip this. So in general, you can use the same trick. It's not really trick, the same identity to calculate any kind of so-called moment of stochastic process. So moment is an expectation value of a product of your stochastic variable, stochastic process. So this is a moment of process process F. So the average value is a moment of order 1, because you have only one instance of f of t. Let's say variation would be a second order moment, or made out of second order moment, if you wish. You can have generally a moment of order n. So formally, you would like to write it as you would take a product of trajectories at different times, f df. But what we learned from this exercise above, you can also calculate it by using our multi-time joint distributions. Pn, Fn, Tfn, Tf1. Okay, and this is something that's actually calculable with standard methods. And it's like any function, you have any function or any functional of your stochastic process, you want to average it, you can always then decompose it into a Taylor, can do a Taylor expansion for it, so you turn into some combination of moments. And now you know that you can calculate your moments using joint distributions. That is, everything is doable with standard methods, standard integration, standard functions. No need to go to those fancy functionals and scary stuff. Okay, so this is like a practical thing. The rest I can skip. Okay, so that was a theory and a little bit of practice of stochastic processes. Because stochastic variables, that was the first step. We'll be using stochastic processes actually down the line, and stochastic variable is actually an example of stochastic process. A stochastic process where all the trajectories are just constant. This reduces to a stochastic variable. Okay, so stochastic processes are the most general, and also you can say. Just normal functions of time are also a kind of stochastic process, but a very trivial stochastic process. So if you have a probability distributions for your process f, that's not really there is no randomness here. So this means that this is like a functional Dirac delta. Okay, so this means that your stochastic process has only one trajectory, f0. So there is only one trajectory, f0 of t, which means that this is just some function of 0. Okay, so even normal functions, functions of time, you can think of them as a stochastic process, just very degenerate stochastic process. Stochastic processes are everywhere, in other words. All right, so maybe you know what? Let's not make a break because we almost we talk about an example and we'll maybe finish a little bit earlier, which probably means that we won't finish earlier anyway. But so that was a theory, and now let's do some practical stuff. Let's consider an example. Oh, it's numbered section 313. Example, famous random telegraph noise. Okay, stochastic processes, often people just refer them to as a noise. Probably heard about white noise. That's a kind of that this is a kind of stochastic process, although very mathematically problematic one. But the other example is a telegraph noise. So what is a telegraph noise? So this is a random telegraph noise, abbreviated sometimes to RTN, random telegraph noise, or even dichotomic noise. Dichotomic means that it's like twofold. So this is a process RT. So I will denote it with R, right? RTN is R. It's such that its trajectories have only two values. So we have trajectories RT, and they have only two values. Conventionally, it's 1 and -1. That would be our standard canonical RTN, is one that has trajectories that's flip between 1 and -1. And the things that characterize this, so we have trajectory that it goes, so let me plot it for you. Time R of t. So you would see something like this, so, and flip, 1 -1. Flip. So it's not a continuous trajectory, but there are no gaps here. Okay, so it's like instantaneous flip. And the thing that characterizes this process is like the rate at which those flips happen. Okay, so when it goes, there is some rate. So when, in the unit of time, there will be like some number of flips in your unit of time, and that would be the rate. Shall we denote here with W, small w, okay? And why am I talking about RTN? Well, because this is one of those precious few stochastic processes for which you can actually write down the joint distributions with analytical formulas. So that's why we talk about it, because it's something we can actually calculate stuff with analytically. So joint probability distributions for our boy here are n. You can write them down as PR T1 R1. So this is like the time one, and here you have a product. So bear with me. J goes from 1 to n -1. And here you have 1 plus Rj times Rj plus 1 times x minus 2 the rate W, Tj minus Tj plus, wait. Other way around. Where is my eraser? Tj plus 1 minus Tj. Because Tj plus 1 is the earlier. I mean, the time goes, Tn is the largest, T1 is the smallest. So it has to be like this, divided by 2. And this formula, this particular formula, works when you're switching between plus and minus values. Okay. And the P1, this guy, the initial dude. So PT1 R1 has another parameter inside, plus R times P times E twice W T1 divided by 2. And this parameter P is something between -1 and 1. Okay. That's what allow. So you have a formula. That's good. That's good. That's good. That's very good. And now you can have variation on random telegraph noise. Variations like so this is like a canonical, let's say, one that flips between +1 and -1 with some rate W. You can have like R prime, for which you have trajectories that have some R plus and R minus values. So not necessarily plus and -1, but some different values. And you can just obtain it by a simple shift of your R of the canonical guy. So you can write it down as R plus minus divided by 2 RT. And you have to compensate with like the average. Okay, so essentially it's a canonical canonical RTN, but you just shift it a bit. Just good to know. There is another one. You can have another random telegraph noise where you switch between -1 and +1, but the rate of switching from +1 to -1 is different than the rate for switching from -1 to +1. Okay? Those guys you can still write down analytical formulas for the joint probabilities, but those are kind of complicated. I won't write it down here. I will leave it for assignment. Okay. Assignment, we'll get to the assignments. Okay, but this is something for you to calculate actually. And those are basically the most useful variants of RTN. So let's just let's do some things with them before the end. Let's get our hands dirty. So I have here 3 assignments, which I decided I will do with you in class, right? Rather than leave it as a home assignment, just to show how this thing operates. So let me flash sorry, I forgot to open the file. Stochastic example. Yeah, so first we go for assignment 16, calculate the average value and the autocorrelation function for random telegraph noise, which I'll explain to you in a moment what it means. Average value is simple. You know what that means. So go back to this, hide. So first assignment 16, as 16. So the average value, average val. So RT bar, which is according to our definitions, 1 plus minus 1, because you have only 2 values, R1, T, R, T1, R1. That's the formula, and we have all the everything is known here, so you can just write down all the values. So that was 1 plus R1 times this parameter P, E2 minus 2 WT1. So the rate. And as you can see, this will be pretty simple. So we multiply this, right? So R1 multiplies, we change cursor. When R1 multiplies 1, some +1 minus 1 just cancels, it just disappears. when it goes here, you get R1 square, which is basically disappears from here because -1 and 1 is the same value. So you are left with P times E minus 2 rate E1. So you can think of this parameter P as basically the thing that determines the average value of your RTM. The correlation function is defined as, we write it like this: correlation function is a two-time thing, so I will use the symbol C, and it's defined as second moment one minus average values. So this is like a variance or dispersion, but with time. Okay. For stochastic variable, there was no time, so it was just x squared minus x squared. Yes, thank you. Yes, very much so. So let's calculate the moment. I mean, those guys we already have. So we know this is P E minus 2W T2. This one is P E minus TW T1. So this is, we already calculated those guys. So now time to calculate moments. Now let's assume here that T2 is greater than T1, because you probably don't remember this, but I said that multi-time probabilities, let's just define them for ordered times, okay? Just a convention we will use here. So R2, R1, R2 times R1, and we need to use here the two-time distribution, R2, R1. But again, we have formulas for that. So let me just use my tuple notation just to make a little bit less writing. Where do I have this? Oh, sorry. R2. Why did I write it like that? Okay, I see. 1 plus R2 times R1 E2 minus W T2 minus T1 divided by 2. I didn't forget about R1, I just write it here. T1 R1. Okay, so that's the formula I wrote for you previously, just to remind that. Okay, it was here. And now we can just do the calculations. So again, first the sum over R2. So it enters, multiplies 1, it just cancels, multiplies this term, R2 square, so it's like disappears. So we will be, so this one will be canceled, right? This one just disappears, right? Because between R2 square, R2 square, where you set R2 to 1 or -1 doesn't matter. It's just the same. It's a constant from the point of view of sum. So you can forget about this. Once you're left with this, so then R1 just multiplies R1, so we have R1 square as well. So what you're getting, you have some R2, R1, plus minus 1, and you have 1/2 R2 square, R1 square, E2 minus 2 W T2 T1 P R T1 R1 which basically means that you can do sum over R2 easily. It will just cancel 1/2 minus 2 W T2 minus 1 because the exponent is just constant, it just depends on time. And we are left with sum over R1 plus minus 1 PR T1 R1, but that's just normalization of single time probability. So we are left with very handsome exponent here. That's cool. So now if we do the calculation when we assume, we repeat this, but we assume that T1 is greater than T2, we'll just get exponent, so R T2, R T1, if you assume that T1 is actually greater, you can just repeat all the steps and you get T1 minus T2. Okay? Quite easily. And just repeat the steps. And so the correlation function, so we can just write it as theta T1, T2, minus T1 plus theta T1 minus T2. So both cases, T1 minus T2, and minus P squared. This is the average square to W T1 plus T2. And well, this we can make it simpler because this just equals to E minus TW absolute value of T2 minus T1. So that's the average and autocorrelation function. And I need to speed up a bit here. So hopefully this is not very difficult. So
more or less methods how much 1 out than after that.
Yes. Okay. This is yes. This is well, how much it depends on the other. That's true, but you can even say a little bit more about it. It's like I like to think of it as like the you have correlation function, so it like tells you if I give you a value of trajectory at time t2, how well can you or maybe no. I give you a value at a time t1, so the earlier value. How well can you predict what the value will be at time t2? Okay, so if the correlation function, because it depends on this distance in time. You know, so it's like if the time is very short, it's almost like 1, let's say, and this means that you can easily predict what the value will be. But as the time stretches, it decays because there is e to minus difference in time, which means that you are less and less sure what the value will actually be because there will be switches, some number of switches. You can just the longer you wait, it's more difficult to predict what happens. So, for example, if you had like degenerate stochastic process in the sense that it's just a function, so a deterministic process, in other words, so that there is only like one trajectory, one specific trajectory, the correlation function would then be like never decay, essentially, because I give you a value, you can like predict what will be the value in the future, right? It's like you just solve your Newton equations and you just, you know, so it's like, that gives you some like, is there some structure in your trajectories, essentially? Or, you know, how they depend, how the values at different times depend on each other. That's also nice. So now let's look at the assignment 17, where we are asked to first to prove this property, which we kind of used in the previous case, and use it to just show that it works like universally for all n, and use it to just calculate arbitrary moments. Okay. So go back to here. So assignment 17. So prove where am I? Here I am. Prove that we do the Rn minus 1, it's 1 minus, Rn times Rn minus 1, PR Tn tuple, Rn tuple, reduces to twice the exponent. So this like indicates that there is some kind of like a fractal structure to our probability distributions here. Okay, so this means n minus 2 means that we have a tuple that has, you know, two last entries are just gone. It's shorted by the two last entries. It just shortens and spits out the exponent, which is pretty nice. So prove this, and this is like some simple calculation. Oh, God damn it. Okay, let me write it down. So we write it n minus 1, n minus 1. So we can, again, pull out our formulas. And they had this, like, this exponent. It was always here. Divided by 2. And when you write it like that, you can actually recognize right? So it's still n minus 1, not n minus 2 here, okay? Before we do the sums, it's still n minus 1. So let me jump to the formula. You see, this is a product, right? So it's like I just took the last factor, right? Take away the last factor, I still has this fractal form. So it just gives me what's left. The remainder is just another probability distribution, right? I just have to check that which times are remaining here. So if you just inspect the formula, you can see that this is true. And again, we have multiplied by two values, sum over. So this means that this identity will just cancel, right? As usual, those guys will pop here, just square. You get n square and minus 1 square. So they behave like constants. So in short, what we are left with e to minus 2 w tn minus tn minus 1, and you have rn minus 1 pr tn minus 1 tuple rn minus 1 tuple. So, and this is, here we can invoke the consistency condition. If you remember, we had this, when you marginalize over any argument, you get a shorter distribution, right? So due to consistency, or you can just write down explicit formulas, but it's nice to invoke the, but this is like a structural thing happening here. Tn minus 2, because we are marginalizing over the last one, so everything just gets shorter. So that's the, so that was task number 1 to prove this. So we have this. And now they asked us, I asked us, actually, I am they, 2 moments. So first there will be a odd moments, because there will be difference between odd and even moments. So now let's start with the even moment. So there are 2k entries here, which again we have, which means that we have to sum over all the r's. Sorry, are 2k r's, 2k, r2k, r1. We have distribution t 2k, 2k. And now I won't get into details here, but you can imagine that you can just iterate this, what we did here, right, over all the steps, right? Okay, you just take a pair, reduce everything, and get an exponent. Take another pair, reduce everything, get another exponent, so on and so forth. Just we can just proceed with this formula here, you know, any number of times we want. So you can imagine that at the end you will be left with all the exponents essentially. J from 1 to k, e to minus rate t 2j. What? Why 2j? Okay, good. 2j minus 2j minus 1. Okay, this is how we can write it. We just exponents that like connect the two timings, two neighboring timings. And for the odd moments, there will be a twist, because our formula works by taking a pairs, right? So you have odd number of r's, there will be one left, right? The last one will be left actually. So you have to like look at that case and take care of it. But once you do the calculation, it's pretty simple to see that it will be just, the last guy will be left T1, like the average value and the exponents. Okay, E minus 2W, 2J. Okay, I found another mistake in my notes. So yeah, simple, very good. So the last thing I wanted to do, but we are running out of time. So maybe I will leave it for later, for next. Yeah, I have to do this. Okay, because I want to talk about Markovian processes. An assignment that actually does the Markovian process. Damn, but then I cannot give you the assignment if I don't talk about this. You know what? Let's do it. Let's do it anyway. It will take us 5 minutes because there won't be too many calculations. So the next assignment number 18. It says check that RTN, so random variable mass, is a Markovian process. That is, using the Bayes law, show that the probability for the trajectory to reach value Rn at time Tn depends only on the value Rn minus 1 attained in the latest moment in past. So only the immediate moment in past. So at Tn minus 1, okay, just before Tn. But not on all the earlier values, Rn minus 2, at Tn minus 2, and so on. So maybe you heard about Markovian processes, Markovian property. It's kind of a popular word. So let me explain what's going on here. So according to Bayes law is about conditional probabilities. Okay, so Bayes law tells you that a conditional probability, which you write like this. So this is a probability that you get the value Fn at time Tn, okay, given that there were, so this is a tuple, bold, the thing that I underline, okay, bold font. Given that at all this previous n minus 1 times, we got values from this sequence, okay? So get Fn given that previous values were all this sequence. So according to Bayes law, this probability is given by the joint probability of getting all the values from F1 to Fn in all those times, corresponding times, divided by the probability that you got the values going from T1 to Tn minus 1. Write this formula. You can treat it as a gospel, okay, at this moment. So now, when you go to RTN, so this is for some general process F, okay. Now we take RTN, for which we know the formulas for probabilities, right? So we can just plug them in. You plug them in, and you realize that almost everything cancels, except for the last factor from the numerator, okay? Because there is one more time in the sequence, so it's this one doesn't cancel fully, and you get this 1 plus r exponent, which we saw so many times, and you can just notice that this guy is actually also equal to the conditional probability where you just have one condition. Instead of whole sequence, there's just one condition. And so this tells us that the probability of getting any value at time Tn does not depend on anything except for the last value in the sequence. Okay, so only on the guy at Tn minus 1. And that's in theory of stochastic processes. This is called Markovian. The process is said to be Markovian if it had this property. And once the process had this property, everything about the process is fully determined by this conditional probability and the probability, single time probability as an initial condition. Why? Well, because using Bayes law, you can just take any multi-time probability like this, and you can just, using this, you can just, start converting it into shorter probabilities. So you have conditional probability times shorter probability, but then you can repeat this process until you reduce everything to just P of T1. So if you know this conditional probability, it's sometimes called transition matrix, and you have given an initial probability, you know everything. You can calculate everything. And this is what actually gave us this fractal-like structure for our calculation of moments, that everything just broke down into those exponents, product of exponents. That's a direct consequence of Markovian property. Yeah, so that's all. That's it. And now homework or assignments for you guys. So we have assignment 18. No, we just did 18, sorry. 19, actually. So if you remember, I told you about this variation of RTN where you switch, the rates of switching are different, right? So the assignment is for you to just calculate those joint probability distributions for this kind of process. And as a hint, there is like a differential equation that governs those probabilities, those transition matrices. So the conditional probability, because all RTNs, all the variations are Markovian processes, so we just need this conditional probability to calculate everything. So, well, the assignment is here. You can always pop to solution and check, consult the notes, okay? And once you have your appetite whet, the second assignment, 20, is actually write a code to generate trajectories of RTN. Okay, so the program you will write will heavily depend on the Markovian property. Without it, it would be like super difficult to write it. But Markovian property, it's kind of easy. Again, solution for consultation. There's even pseudocode here if you want to cheat. But take a look at this and plot for your own pleasure, a couple of trajectories. And yeah, and that would be it for today.